Okay, we'll get started now. The first exam is in the books. I took a quick glance at the results. It was pretty good. Our average was at least a little bit higher than the last time I taught this course, so I'll have to take a deeper dive a little bit later and show you some of those results next week, but everything looks good. Now, obviously, some of you are going to be happy with the results, and some of you won't be, and the first exam doesn't determine anyone's grade, so if we need to keep working hard if you did well, but obviously if you're not happy with how things were, come talk to me and we'll try to figure out what you were missing and what you might need to do in the future to improve things. So there's still a lot of time left in the semester. Okay, so today we're going to talk about, we're going to start chapter 5. So the course is about to take a pretty abrupt turn in terms of the style of the content and the types of problems that you're mostly going to be doing. So up until now, we've kind of been building up mostly at a conceptual level from single atoms up to two atoms bonded together, and then molecules that are more complex than that, talking a lot about the arrangement of electrons and the structures of the molecules, things like that, all at the sort of microscopic, atomic, and molecular level. So what we're going to transition to now into chapter 5 is talking about sort of larger ensembles of chemical substances and how they react with each other, how we can quantify chemical reactions, how we can quantify other physical properties that are either inherent to the substance itself or also related to a reaction that's happening. So it's going to be now, not thinking as much about individual atoms and molecules, although the sort of relationship between what we're going to do now and all that microscopic level atoms and molecules stuff that we've been talking about until now, that relationship I think is pretty interesting and try to understand it, and that's really what makes chemistry fascinating in my opinion. But it's going to be a lot different, so if you like mathematical problems, then this part of the course is going to be your bread and butter. If you are afraid of mathematical problems, well, then you just have to adjust yourself and get ready because they're coming. So the first thing we're going to talk about is atomic mass and moles. So that's really the topic of today's lecture. So we've talked about mass number. Atomic mass is closely related to the mass number. Remember, we define mass number as the number of protons plus neutrons in the nucleus of an atom. And atomic mass is closely related to that. But we're going to now start thinking about it as an actual mass, a way of actually measuring out substances. Now, at the individual atomic level, we have what's defined as an atomic mass unit, which is approximately equal to the mass of a proton or a neutron. So the mass number is going to be approximately equal to the atomic mass of that isotope, but it's not exactly the same, and we'll get into the reasons why a little bit. But an atomic mass unit, AMU, is defined as the mass of the 12 carbon isotope divided by 12. All right, so again, that's sort of the standard that was chosen. I don't know who the powers that be were that chose that or why they chose that, but that's a very common isotope in natural world. And they chose that, they measured its mass, and they divided it by 12 to find 1 AMU. All right, so this is again the standard. 12 carbon, all atomic masses are sort of measured relative to that. We can't easily measure the mass of an individual atom, but we can sort of set a standard and measure relative to that. And we're not going to get into how you measure atomic masses, but essentially a common way of doing it anyway is to ionize the sample and put it through an electric or magnetic field. The ions will be deflected by the electric field, and the amount that they're deflected is related to their mass. So again, you measure it relative to 12 carbon, which you set as exactly 12 AMU, and the relative deflection of anything else is going to tell you the mass of that atom either being bigger or smaller than 12, and how much bigger or smaller is a factor. Anyway, so for when we measure atomic masses, as we said, it's relative to C12. So you can measure ratios of masses pretty easily, as I said. There's a few different techniques for doing that where you can get a ratio. So if we did carbon-13, which is another isotope of carbon that has just one more neutron in the nucleus, we know the mass number is 13, but let's figure out what the atomic mass is. So the measured ratio of these two is 1.0836. Again, that's an experimental number, not one that you can come up with any other way. And then what we do is we just do a little algebra. We multiply this times 12 to get the actual mass of C13. And what you'll notice, even for this isotope, which is very similar to C12, it's not exactly the same as the mass number. It's 3.0032 AMU, a little bit bigger than 13. Again, if mass number and atomic mass were exactly the same, this number would be exactly 13.0000, however many. But there's a little bit of a difference, and as you go to isotopes that are further away from C12, their atomic masses get even further and further away from their mass number. Not usually by a ton, still within a decimal place or so, but nonetheless there's a small deviation. So why is that? This is not a huge topic for this course. It'll be maybe covered a little bit more detail in Chem 2. But essentially, why is the atomic mass not equal to the mass number? It's because of this famous equation here. Again, a scientist we've talked about before, who you've probably heard of, Albert Einstein. And so one of the implications of this equation, E equals mc squared, E is energy, m is mass, and then c is the speed of light. One of the implications is that when you form a nucleus, you have protons and neutrons coming together, forming this densely packed nucleus that's at the center of an atom, a lot of energy is released when that happens. So when you form a nucleus by bringing together some number of protons and neutrons, it releases a lot of energy. And that energy is large compared to the mass, because again, the mass of individual nuclei are small. And because of this relationship between energy and mass that Einstein came up with, that release of energy changes the mass from the ideal whole number value. Okay? So that's kind of the origin. Again, we're not going to really hold you too responsible for that. But that's why these atomic masses are not exactly equal to the mass number. It's important to realize that. And then the other parameter that we can define then for any element, so every element is going to have certain numbers of isotopes. In most cases, naturally occurring elements have more than one isotope that they're comprised of. So if you have a block of carbon, which like graphite is a form of carbon, or diamond if you're if you're blinging out today, when you look at pure carbon, it's going to have a mixture of carbon 12 and carbon 13, maybe a little tiny bit of carbon 14 too. But every element is going to have some mixture, some distribution of isotopes. And so we define the relative amount of each by the percent abundance. So it's going to be the relative amount of each isotope in a naturally occurring sample of that element. Now this is not a mass ratio, this is a ratio of, I guess, the number of each type of atom that you would have in that element. So for example, if we have carbon, as we just talked about, carbon 12 makes up about 98.89% of naturally occurring carbon. All right, so when you have carbon, whether it be in the form of a diamond or a graphite, or whatever form of carbon you have, 98.89% of those atoms in that sample are going to be carbon 12, 6 protons, 6 neutrons in the nucleus. But then the rest of that, to 2 decimal places anyway, is going to be C13. So the remaining 1.11% of those atoms is C13. So roughly 1 out of every 100 carbon atoms is C13. So every element is like that. I mean, there are some elements that are 100% single isotope. I'm sure that's true for some of them, but almost every element has measurable amounts of 2 or more different isotopes that make that up. And so then what we can define is what's called the atomic mass. So the atomic mass for an element is the weighted average of all the isotope masses. So we talked about the individual isotopes having a mass that's close to the mass number, but not exactly that number. But then if we average all those together as weighted by the abundance, we can get what's called the atomic mass for that element. All right, so it's a weighted average of all the isotope masses for that element. So the way you calculate it is you take the fractional abundance of one isotope, which I'll call A, multiplied by its mass. So again, fraction is just percent divided by 100. So you take these percentages, which is how they're normally reported, and divide it by 100 to get it into a ratio or a fraction. You take that, and then you add to that the fraction of the other isotope, multiplied by its mass, And you do that for however many isotopes you have, where the sum of the fractions will equal 1 or 100% as a percentage, and then the individual masses have to be accounted for when you do this weighted average. So the way, the problems that you'll see in homework assignments and tests will probably not go more than 3 isotopes, but nonetheless you can do this for however many isotopes there are for that particular element. All right, so that's the definition. So then let's go through a couple of sample problems related to this concept. This is really the first type of problem we'll see in this chapter that'll come up on homework assignments and exams, which is using the definition of atomic mass in 2 different ways. All right, so if you look at this problem here is a more straightforward one where we're giving you the masses and the abundances of 2 isotopes. So this is the element boron. Just like carbon, it consists of 2 isotopes, but the ratio is different. So it's about 20% boron 10, it's about 80% boron 11, and we want to know what is the atomic mass of boron, which again is the weighted average of those isotope masses. All right, so to write out that sort of relationship again, the atomic mass is going to be the weighted average of all the isotopes. So it's going to be the fraction of the first isotope, which is 10 boron, multiplied by the mass of that isotope. And again, you can see that those masses are close, but not exactly equal to the mass number. And then we're going to add to that the fraction of the second isotope, which in this case is boron 11, multiplied by the mass of that isotope. So putting the numbers in, there's really no algebra here, we just have to put those in. Now again, the only difference though is remember that we're giving you percentages, which are out of 100, but for this equation we need to use the fraction, which is out of 1. So the fraction of each is going to be the percent divided by 100. So the fraction for 10 boron is going to be that percentage, 19.90, but then divided by 100. So in this part of the course, in a few different contexts, you'll get pretty good at dividing by 100 in your head. So for boron 11, we take that number, 80.10 divided by 100, so it's going to be 0.8010. And we are doing problems, one sort of, we've done a few numerical problems, but most of them are not too many steps. But in this part of the course, we're going to do a lot of multi-step problems, this one just being a couple steps here. But I always encourage you, don't do any rounding until the end. I mean, you can do a little bit of rounding, so you're not keeping like 20 decimal places. But keep at least a couple extra significant figures, 1 or 2 extra significant figures as you go through to make sure you're not rounding too much. So here we're going to not do any rounding until the very end. And then if we want to find the atomic mass of boron, we just plug all those numbers in. So it's going to be the fraction of boron 10, which is 0.1990, multiplied by its mass, which is here given as 10.01294 AMU, plus the fraction of the second times its mass, and what that comes out to is 10.811 AMU. So this would be how we would report the atomic mass of boron, which is a weighted average of, in this case, the 2 isotope masses that we have. And this is the number that's on the periodic table. So we haven't used that number, the other number on the periodic table we haven't used yet, but that's what we're showing. So for boron it's 10.81. If we go to the periodic table for boron, we'll see that that's exactly the number that's reported underneath the atomic symbol, 10.811. So that's what that second number refers to, is the atomic mass, which again is the weighted average of all of the isotopes, which is again why pretty much none of these are whole numbers, because it's a weighted average of more than one isotope, and those isotopes themselves are not whole number masses. Now, the other thing too to keep in mind is in some problems we won't give you the exact isotope masses. So here we gave it to you as 10.01294 and 11.00931. If we don't give you the exact isotope masses but still want you to approximate the atomic mass, then you would just use the mass number. So we didn't give you the exact mass, we would just use 10 for boron 10 and 11 for boron 11, which is close, and it'll give you at least a good approximation of the atomic mass. But in other cases like we did here, we'll give you the exact isotope masses, and in that case, that's what you want to use, okay? So any questions on that? All right, the next one is just a variation on this, but just solving for something a little bit different, so using a little bit of algebra this time. So here what we're doing is we're taking another element, chlorine, and we're giving you the atomic mass. So we're giving you the weighted average mass. And we're telling you here that it has 2 naturally occurring isotopes, and we're giving you, again, the masses of those isotopes individually, 35 chlorine and 37 chlorine. We want to know what is the percent abundance of the isotope 35. So here we're not solving for atomic mass, we're giving you atomic mass and asking you to solve for one of the abundances. So in problems like this, you're typically going to have to set up 2 equations with 2 unknowns, because we don't know the abundance of either isotope right now. So we have 2 things that are unknown. That means we need 2 equations to solve them. That's basic algebra. So what we're going to do to keep things simple is we're going to define the fractional abundance of one of the isotopes. I'll call it 35 as x. So we'll just use x and y here to make our algebra a little bit simpler. And the fractional abundance of 37Cl we'll call y. So those are going to be our 2 unknowns. We don't know either of those at the start, and we're trying to find one of them to answer this question. So the first equation we're going to set up is going to be just the definition of atomic mass, where we take, this is the given atomic mass, 35.45, and that's going to equal the fraction of each isotope multiplied by the mass of each isotope. So the fraction of 35 is x, the mass of 35Cl is 34.96885, so that's going to be the first term in that equation. I'll put x at the end because that's more conventional, but so that's again fraction times mass plus fraction times mass for the second one, which the fraction of that one we're calling y, and the mass of 37Cl is 36.96590 and y. All right, but obviously we can't solve this equation with just one equation, 2 unknowns, but we always have to remember the other relationship that we'll have is that the sum of the fractional abundances has to equal 1, or alternatively the sum of the percent abundances equals 100%. So whenever you have a mixture of isotopes, whether it's 2, 3, 4, or so on, all the fractional abundances add together equal 1, or 100%. So in this case it's just 2, so the second equation will just be that x plus y equals 1. Okay? So the sum of the fractional abundances equals 1 for any system that's defined in this way. And what we're going to solve for here is we're looking for 35Cl, which is x, so we're going to solve for y in this equation, 1 minus x, and then put it back up here. There's more than one way that you could solve this equation, set of equations, of course, but I think the more straightforward way is to do it this way. Replace this y with 1 minus x. And so that gives us this equation here. 35.45 is equal to, the first term is the same. And then for the second term, we have the mass of 37Cl, and we're going to replace y with 1 minus x. All right, and so then we can do the algebra, which I'm going to skip over and just put it in the algebra machine, and we get x is equal to 0.7590. What we wanted was the percent abundance. Anytime you're talking about percentage, you have to multiply by 100. So the percent would be this number times 100, which is 75.90. And that matches choice C. Okay, so that means the other isotope, this is almost 76%, the other isotope is a little bit over 24%. So again, they add up to 100%. All right, so that's how you would solve a problem like this, where we're, in this case, asking you to solve for an abundance. It requires some algebra, but it's the same concept, same basic equation that you're starting with. All right, any questions? All right, so that's kind of giving us the definition of atomic mass, but really the major use, the major importance of atomic mass is its relationship to what's called a mole. So I want to start by helping you understand what a mole is. I mean, if you've taken chemistry before, you've already seen this, and you know, it's not the animal. That's the spoiler alert. The mole is not the animal in this case, but it is what it is in chemistry is a counting word. So we have a bunch of counting words in the English language. I don't know if they're common in other languages, but in English we use them. So a dozen would be 12. A gross would be 12 dozen, which is 144. That one's not as common. Another one that's kind of old school, but if you're familiar with the Gettysburg Address, when he said 4 score and 7 years ago, a score means 20. So that was 87 years ago. So a score means 20. So we have these different counting words in the English language that tell us how much of something we have. And a mole is just a counting number. It tells us how many things we have, whatever those things are. Usually a thing in the context of a mole is an atom or a molecule, of course. But it's just a counting number that tells us how much of some entity we have. But the number is huge. It's not 12, 144, or 20. It's 6.022 times 10 to the 23rd. And again, we can count anything with moles. But atoms and molecules, of course, are the most common things that we count with moles. And this number here is called Avogadro's number. Now, the story that I heard about Avogadro's number is that Avogadro didn't actually come up with Avogadro's number. He had a bunch of other important discoveries, one of which we talked about a little bit at the beginning, and we'll come back to in a couple chapters from now. But whenever they came up with Avogadro's number, they just had a huge man crush on Avogadro and decided to name it after him. But it's not actually his number. But it is important nonetheless. And it's, again, the number that tells us how many things are in a mole. It's a counting number. Now, the next slide here is kind of just for fun. And I guess we're allowed to have a little bit of fun in here, if that's okay with you guys. But we're going to talk about, just give you an idea of how big the number, Avogadro's number, 6.02 times 10 to the 23rd. How big of a number is that? Okay, so let's say we're going to take 1 mole of M&Ms and stack them over the entire United States of America. And let's figure out, how many times we have to stack those M&Ms to get to the, if you're, the lights just turned on, so. The ghost is back in the room. All right, so we're going to figure out if we stack M&Ms over the entire continental United States. I forget if this counts Alaska, but whatever, it's the same story. And figure out how high do we have to stack these M&Ms if we're using a whole mole of M&Ms to cover the United States. So just a little bit of back of the envelope approximation here, not exact, but gives us the right order of magnitude. The volume of one M&M, let's say that's about a cubic centimeter. That's probably overestimating a little bit, but it's close. And then we can say that the area of the United States is 3.02 times 10 to the 6 square miles. So again, you're not expecting to know these numbers, we're just giving them to you and and then we do a bunch of calculations. We figure out the volume of the mole of M&Ms, the area that they're covering, and then how high do we have to stack those to fill that volume. So anybody want to guess how high would the layer of M&Ms be if we're putting a mole of M&Ms over the whole United States? Things like 1 layer, a few layers. How high do you think it would be? Any guesses? 10 layers. Okay, we're going with 10 layers. I think you undershot a little bit. So it turns out that the height of the stack of M&Ms, I don't even know how many, I have the number of layers here in a second, but it's going to be 50 miles tall. And that corresponds to 8 million layers. Yeah, so hopefully you understand how big the mole is now from that. So it's a gigantic number, a number that we can't comprehend on the human length scale and time scale and all that stuff. It's just gigantic. And again, that's because, as we've kind of already talked about, individual atoms and molecules are exceptionally tiny. So if we're counting those and we're trying to relate that to some quantity that's useful for us, we need to count a lot of those to get a useful quantity. So we don't really use, in chemistry, we don't use Avogadro's number a lot. Like, we're not usually interested in how many individual atoms and molecules there are. Of course, we're going to ask you guys to use it because it's part of any general chemistry course. But in reality, it's not the most common way that we count things. But again, you want to understand what it is. And we're going to what we're going to do for a lot of the rest of the course is relate the mole to other quantities that we can measure that are more useful for us. All right. So then we can also do another comparison to just tell you how big the mole is. So let's figure out how many teaspoons of water are in all of the world's oceans. So let's say we take a teaspoon and we're scooping out all the water from the oceans in the world. So the volume of the oceans, you have to do some conversions to get this math right, but it's like 1.3 times 10 to the 9th cubic kilometers, which is huge, right? But there's that corresponds, if you do the conversion factors, to about 2.65 times 10 to the 23rd teaspoons, which is about a mole. So basically, there's 1 mole of, so there's, the number of teaspoons in the whole of water in the whole world is about 1 mole. All right, so again, that tells you how huge that number is. And another cool thing is that there's more teaspoons of water in the world than there are, or about the same number as there are molecules of water in a single teaspoon. So again, that, you know, one little spoonful of water has close to a mole of molecules, which is how many teaspoons are in the entire world. So just kind of another one to sort of wrap your head around how big that number is. I think the first one is perhaps even more impressive. Okay, so that's how big a mole is, but that was again for fun. But what we really wanted to is talk about how we use the mole in chemistry. All right, I guess the lights just want to be on today, so we'll leave them on. Oh, it's like really bright. Now that like stuff is beeping too, it's just, this whole room is falling apart. I don't know what that beeping noise is. The light controls are, I think, are what's beeping up here, but what does this do? This might turn on all the lights. I don't want to do that. Let's try one more time to get it how we like it, and then if not, we'll just leave it. Okay, so what we're going to start with first is going to be a big part of this chapter, chapter 5, is the relationship between atomic mass and moles. We just defined atomic mass, we just defined moles. Those two are closely related to each other. And so there's an alternative interpretation of atomic mass. We said atomic mass in AMU can be thought of as the mass of an individual atom for a specific isotope, and then when you average those together, that's sort of the mass, the weighted average mass of the whole sample. Now all the lights are out, so all right, let's just leave it like that and see if it's happy. All right. Okay, so anyway, the alternative interpretation of atomic mass, though, is that it represents the mass in grams of 1 mole of an element. Sounds like there's some activity going on outside the room, so I don't know if they're messing with us, but for those of you that are watching this, again, I'm not like freaking out up here. The lights are going on and off in the room, and everybody who's here. So if you want this level of entertainment, you need to come to class. You can't get this on YouTube, but all right. So the atomic mass represents the mass in grams of 1 mole of an element. So that's the alternative and more useful interpretation of that number. Okay, and so like we saw the atomic mass for we did boron earlier was 10.81, and so that means if you have 10.81 grams of boron, you have exactly 1 mole of boron, or 6.02 times 10 to the 23rd boron atoms. So those are related to each other. So at this point, we have 2 conversion factors involving the concept or the quantity mole. We're going to build up more of these as we go through this next part of the course, especially in the next couple chapters. But the 2 big ones for this chapter are Avogadro's number, which tells us how many atoms or molecules, or even more generally, things we have in 1 mole. Again, you can count anything with a mole, but it's usually going to be atoms and molecules. And then the other one is the atomic mass, which is you have that many grams of an element in 1 mole of an element. All right, and you'll notice I'm using MOL here, so that's the abbreviation for mole. It's the world's stupidest abbreviation because they just take off 1 letter and don't change the number of syllables. It's kind of like H-Town is an abbreviation for Houston, but nonetheless, that's the abbreviation for mole, MOL. So just be used to that. All right, so let's do some sample problems that are going to involve these 2 relationships. And we want to start thinking about these relationships that I've given you as conversion factors that allow us to convert between one quantity of a substance and another using the mole as kind of that sort of linchpin quantity. Okay, so let's say we have a helium cylinder, which is becoming more and more difficult to find as the shortage of everything continues. And a helium cylinder would contain 239 moles of helium, and we want to know how many helium atoms are in the cylinder. So this is a pretty simple, one-step conversion, where if we're looking for number of helium atoms, the way we're going to set it up is we're going to write out what we're looking for. We've done a few problems like this, but now it's going to become the very common approach, which we call the factor label method. So I like to start out with what we're looking for, which is the number of helium atoms. We start with what we're given, which is 239 moles, and then we have to figure out which relationship or relationships we will need to be able to convert that to the desired quantity. So if we have moles and we're trying to count how many atoms there are, we should immediately think of Avogadro's number. And we're going to write it in this way. We're going to multiply by 6.02 times 10 to the 23rd because we want to have helium atoms in the numerator and we want to cancel out moles in the denominator. Okay, so moles cancel out. That gets us into how many helium atoms we have, which is what we're looking for. And that number is just 1.44 times 10 to the 26. Okay, I'm going to attempt one more time to put the lights how I like them because I think it stopped beeping, so that might mean that it's happy now. All right, now let's see if it stays. All right, so that's how many helium atoms are in a helium cylinder, and again, this claim is just a one-step conversion using Avogadro's number. So to sort of wrap up and summarize this type of problem, if you're counting individual atoms or molecules, so if we say how many atoms or molecules are in something, you should automatically think of Avogadro's number. So use Avogadro's number. And it's important also to remember that the identity of the substance doesn't matter. There's one Avogadro's number. It applies to every substance in the world. The only thing you have to keep in mind with Avogadro's number is what exactly are you counting for that substance. So in this case, helium is just made up of helium atoms, just He atoms all floating around. And so when you multiply how many moles of helium you have by Avogadro's number, that tells you how many helium atoms you have. Now other gases, as we'll talk about in more detail later in the course, like nitrogen, is N2. So if you have a cylinder of nitrogen and it has the same number of moles, you would get the same number, but that time it's not nitrogen atoms, it's nitrogen molecules, N2 molecules. So it's however many of that fundamental unit you have that makes up that substance. So if it's an element, it's very often going to be atoms, but for other types of elements or for any type of compound, it's going to be molecules, and so you have to think about what that number means, but it's really the same number for all substances. Just the meaning is slightly different depending on what that substance is made of. All right, let's just do one other one, which is another simple one-step problem. So if we have a gold bullion coin, it contains 31.1 grams of pure gold, which is atomic symbol AU. We want to know how many moles of gold are in the coin. All right, so again, we're looking for moles this time. And we write down what we're looking for, which is moles. We write down what we're given, which is 31.1 grams, and then we figure out how to convert those two quantities. All right, so we have 31.1 grams of gold. And we should recognize that the relationship between grams and moles is going to be the atomic mass in this case. So to make sure we do it right, let's write out our units. So we want moles of gold in the numerator, and we want to cancel out grams. So the relationship that involves grams and moles is going to be the atomic mass. Now we didn't give you the atomic mass here, but remember it's on the periodic table. So we go back to the periodic table, we find gold right there, number 79, and that number below is the atomic mass, 196.97. So that's grams per mole of gold, but we want the grams to cancel out, so that number is going to go in the denominator, 196.97 grams in 1 mole. Okay, so in this case we had to invert that to get the units to cancel out properly. And what that leaves us with is 0.158 moles. All right, so this is a classic example which we're they're not always going to be simple one steps like this, but in a very common step in many problems we're going to do is converting between mass and moles. In that case, you use the atomic mass. So in this case, you do need to know the identity of the substance, though, because every substance has its own, we're talking about elements for now, but we'll do it for compounds later. Every element has its own atomic mass, so in this case, it does matter what that is. There's not a single relationship, like Avogadro's number. So we had to know that it was gold and use the appropriate atomic mass for gold, which would be different for every element on the periodic table. So that's going to be, again, a slight difference, but still just a one-step relationship between grams and moles. So any questions so far on those relationships? Again, they're going to be very important for this whole chapter, especially this one here, grams and moles. So we want to make sure we're comfortable with that so we can start using it in more complex settings. All right, let's just do a couple other example problems that involve multiple steps, so kind of combining the two things we just did. So this, I guess, isn't so recent anymore because I made this slide a long time ago. But anyway, there's someone that I know who I went to grad school with discovered this nanoparticle that has a 1.3 nanometer diameter, and they determined that there's 37 indium atoms in the structure. So we want to know what is the mass of indium in grams for one of these particles. So in other words, a simpler way is what is the mass of 37 indium atoms in grams. So how do we figure this out? So we're looking for grams of indium. Again, write out what you're looking for. And what we're told is that we have 37 atoms of indium. The 1.3 nanometer diameter doesn't matter. The size of the particle that those indium atoms are arranged in, we don't really care about that. We know if we're starting with 37 indium atoms, we're going to try to figure out how many grams are in that quantity. But in this case, we don't have a simple one-step conversion. We don't know the mass easily of an individual atom of indium. We can look it up, but we don't have that number very easily available to us. So this is going to be a two-step conversion. Let me actually move it down so I don't interfere with that graphic over there. So just cross it out because sometimes erasing makes my tablet spaz. All right, here we go. So we're looking for grams of indium. We're given 37 atoms as our starting point. And this time we need a two-step conversion. So usually if we're doing multiple step conversions, we're going to go through moles as sort of that linking type of quantity because we have a bunch of relationships involving moles, 2 now but more to come, and so we want to get to moles first is usually how we're going to do things. So if we have atoms of indium, if we know how many indium atoms we have, the number of moles we have is going to be determined by Avogadro's number. All right, so again, to make sure we write it out correctly, we want atoms in the denominator, moles in the numerator, and Avogadro's number tells us that 1 mole has 6.02 times 10 to the 23rd atoms. All right, so again, it's important to make sure we write these in the correct way, that we put Avogadro's number in the denominator this time because we want to convert atoms into moles, and that's how we would use that number. But this is not the stopping point because now we have moles, but we're looking for grams. But again, if we're looking for the relationship between grams and moles, that's the one we just covered, which is atomic mass. So we want grams of indium in the numerator and moles in the denominator, and we have a simple relationship, atomic mass, that relates those two. So we need the atomic mass, which again comes from the periodic table. We didn't give it to you, but this is an element, and so it's In 114.82 is the atomic mass. All right? So that's the number we're going to use to go from moles into grams, and this time we're going to multiply by that number because we want moles to cancel, and we want grams then to be the final quantity that we get. So once the units match, that's why I always encourage you to write out units because it's easy to know when to stop. The units now match, grams of indium is what we're looking for, so then we can just multiply across. And we get a very small number because we're talking about a very small collection of indium, only 37 atoms. So it's 7.05 times 10 to the 21st grams. Again, very tiny number now because there's only a few atoms, or a few dozen I suppose, but not a huge number. All right, so that's how we would use those two conversion factors together. That's one way we can use them together. So very often you're going to have to use both of those or other combinations of conversion factors that we'll cover later on, so it's not always going to be one step. And then any questions on that, I guess, before I move on? All right, then the next one is just another variation. So now we're talking about a whole bar of gold. So a bar of gold weighs 12.4 kilograms. We want to know how many gold atoms are present in that. Okay, so again, let's write out what we're looking for. We're looking for how many gold atoms we have. And we're starting with a quantity 12.4 kilograms. All right, so we don't, again, have a simple relationship for mass and number of atoms, but we can do it in two steps just like we did the last one. So if we know the mass of a substance, we can figure out how many moles of the substance there are first. Again, you usually want to think about getting to moles as fast as you can in a lot of these types of problems because that's going to be the quantity that relates a lot of things. And then once we have moles, we can get into number of atoms using Avogadro's number. So again, two steps. So the only thing we have to be a little bit careful with here again is units, because we're giving you mass in kilograms, but the atomic mass is grams per mole. So you have to make sure your mass is in the correct unit before you just start multiplying. So we have to get to grams first. We don't use kilograms a lot in chemistry, it's a pretty big quantity. But if we want kilograms to cancel, and we want to get into grams, that's going to be 1,000 grams per kilogram. Kilo means 1,000. Now that we're in grams, we can use the atomic mass to go to moles, and that's going to be the next step. And again, to make sure we do it right, I like to write out the units first. So we want grams to cancel, and that means that number is going to go in the denominator. As we saw in the previous problem, or a couple problems ago, the atomic mass of gold is 196.97, so this time we're going to divide by that, which I think we did last time also. So that gives us into moles. That's 196.97 grams in 1 mole. And that's, again, not our starting point, though, because we're looking for the number of atoms of gold, not the number of moles. And so that's where we're going to use Avogadro's number. Just to get used to it, how I'm going to do it, a lot of these multi-step problems, I'll have to do them on more than one line, so I'll just continue on to the next line, so don't be confused by that if you're looking at the notes later on or trying to follow what I'm doing. So we're going to go to the next line and use the last conversion step, 6.02 times 10 to the 23rd. I should have written the units first like I always like to do, and I didn't here, but this is the correct way to do it because we want moles to cancel. We want to figure out how many atoms there are, so we're going to use Avogadro's number in the numerator. And so we get 3.79 times 10 to the 25th atoms. So again, a very big number. All right, it's not, as I said, very common in chemistry that we need to count how many atoms or molecules there are in a sample, but we can do that once we have Avogadro's number, and we can also relate it to mass using this type of two-step relationship. All right, questions so far? All right, then the next thing we're going to cover is going to be what's called more generally the molar mass. So we talked about individual elements now, where their atomic mass, straight from the periodic table, is going to tell us how many grams of that element are in 1 mole, and that's a very useful relationship. But we want to generalize it more and talk about a mole of any substance. So if it's not an element but it's a compound, what's the relationship that gives us between mass and moles for that? And it's a quantity that can be generally called molar mass. Sometimes it's called, there's other names for it, so I'll give those here in a second. But the definition of molar mass, very generally, is the mass of 1 mole of a compound. I suppose you could even write it more generally and just say molar mass is the mass of 1 mole of a substance, which can be a compound or an element. It's in grams per mole. For an element, the molar mass is the atomic mass. Because again, the atomic mass is the mass of 1 mole of an element. But for a compound, it's going to be defined a little bit differently and calculated a little bit differently, but not pretty straightforward, as we'll see. Now, there are synonyms for this, so we can use the general term molar mass, and that's probably what I'll use most often, just because it's so general and applies to any substance. But you might see some other things as well. So especially for covalent compounds, we'll use the term molecular weight a lot. Or sometimes it's called the formula mass or formula weight. That's common for ionic compounds. So those are some different ways you might hear it referred to, but it's just the same thing. It's the mass of 1 mole of that substance, whether it's called molar mass, which is the most clear terminology, or molecular weight or formula mass. Formula weight, all of those represent the mass of 1 mole of the substance. And there's some abbreviations you might see. I don't think this one you'll see anymore. The old textbook had it, and by old I mean like the one we used like 5 or 7 years ago when I was first starting here. So there's like a big script M, which I can't even draw properly. So if that shows up in any homework questions, like a big, I can't even draw it. It's like a big capital M, but it's like slanted and all cursive looking, which I haven't written cursive since I was like 10 years old, so I forget how to do it. And then the other one you might see, because of the common usage of molecular weight, is MW for molecular weight. So that's another abbreviation, but they all mean the same thing. And in context, it should be pretty obvious what that number is important for. Now, the way that we calculate it for a compound or anything that's not just a simple element is we just add together the individual atomic masses. So it's not hard to get this number at all. It just takes a little bit of extra work. because we'll know the formula of the compound, we'll know the atoms that make up that compound, and just adding together the individual atomic masses is going to give us the molar mass of that compound. Still blinking a lot. All right, so that's how we calculate molar mass for any substance. Okay, so let's go through and just, again, a lot of these types of concepts are best worked out with example problems. So let's say we have glycine, which is one of the simpler, maybe the simplest amino acid. And we want to know what is the molar mass if we know the chemical formula is C2H5NO2. All right, so when we're calculating molar mass, what we have to recognize from the chemical formula, what do these subscripts mean in terms of moles? So we haven't really interpreted chemical formulas before in terms of moles. We've always interpreted it as 2 carbon atoms, 5 hydrogen atoms, 1 nitrogen, and 2 oxygens. We could potentially draw the Lewis structure, although this one's pretty complicated. But we can also interpret chemical formulas in terms of the moles of each component. So if we have 1 mole of this compound, C2H5NO2, the subscripts in the chemical formula tell us that for every 1 mole of compound, we have 2 moles of carbon, 5 moles of hydrogen, those are just the subscripts for each element, 1 mole of nitrogen, and 2 moles of oxygen. Okay? And so again, what we do then to find the molar mass of a compound like this is just add up the atomic masses of all the elements that make it up, accounting for how many of each atom we have. So the molar mass of this substance is going to be then 2 times the atomic mass of carbon. So we have 2 moles of carbon, we need the atomic mass of carbon. So that again comes from the periodic table. So carbon is 12.011. We're going to do also hydrogen, which is 1.008. I don't want to flip back and forth a million times. So we're going to have carbon, hydrogen, nitrogen, which is 14.01, and then oxygen, which is pretty much exactly 16. So those 4 elements, but different amounts of each one. So when we calculate the molar mass, we have 2 carbons in the formula, so we're going to multiply the atomic mass of carbon by 2. All right, so that's the atomic mass of carbon multiplied by 2, because this substance has 2 moles of carbon and 1 mole of the substance. For hydrogen, there's 5. Coefficient or subscript of 5, so it's going to be 5 times the atomic mass of hydrogen, which is the smallest one, 1.008. And then we're going to add to that, we have 1 nitrogen, so it's going to be 1 times the atomic mass of nitrogen. And then we have 2 oxygens as well, so it's going to be 2 times the atomic mass of oxygen, which to 2 decimal places is 16.00. So we just add all those numbers up, 2 times 12.01 plus 5 times 1.008 plus 1 times 14.01 plus 2 times 16, and we get 75.07 grams per mole. All right, so that tells us for glycine, which has this given chemical formula, 1 mole of the substance will have a mass of 75.07 grams. So it's pretty straightforward, and down the line, when we're doing more complicated problems, we'll often just give you the molar masses so you don't have to spend the time calculating them every time. But this is how you would do it anytime you need the molar mass of a compound where you know the formula. All right. Let's just do some more. All right, so this one here is, determining the formula mass of lead-4 sulfate. So this requires us to remember our nomenclature for ionic compounds. We can't forget everything we learned in the first 4 chapters, even though things are a lot different in this chapter. So if we give you the name of a compound, in many cases you should be able to come up with a formula, because if we want the formula mass, which again is just a synonym for molar mass, we need the formula of the compound, obviously. We can't just get it from the name. So here we have lead and sulfate, lead-4. So that tells us that lead, which is, I guess I should have told you that lead is Pb. It's not one you have to remember because it's too far down the periodic table. But lead is Pb, and the 4 tells us that it has a +4 charge. And then sulfate, we have to remember, is one of our polyatomic ions, which is SO4 2-. So when we want to get the formula of this, again, we can take the the charges and make them subscripts. So we would get Pb2 and then SO4, 4, but we want that to be the simplest ratio, so instead of 4 and 2, we write it as 1 to 2. PbSO4 to balance the charges with the smallest ratio of ions. So that's the correct formula for lead sulfate, PbSO4. But then what we have to remember is when we're calculating the molar mass of the substance, you have to account for how many of each atom there are. So if we want to find the molar mass, or the formula mass, as it's termed here, but they mean the same thing, and they're calculated the same way, we have 1 lead in the formula, and the atomic mass of lead is down here, 207.20. So that's the mass of lead. Now, one of the reasons I did this example problem, even though it's quite a little bit similar to the last one, is make sure we're counting the number of atoms correctly in this formula. So remember, SO4, that means we have 2 whole sulfate sulfate ions in the formula. So that's going to be SO4 taken twice, which means we have a total of 2 sulfurs and 8 oxygens. Each sulfate is 1 sulfur, 4 oxygens. We have 2 of those all together. That's what that little subscript means. So it's going to be a total of 2 sulfurs and 4 oxygens. So for sulfur, we need to take 2 of them and account for that in the formula mass. And the atomic mass of sulfur is right below oxygen, 32.07. Usually 2 decimal places is perfectly fine, even though it's given to you with 3. And then oxygen is up here, 16 again, that we saw last time. So we just have to make sure that we count the number of those correctly. So there's 2 sulfurs in the formula because there's 2 whole sulfates. And then for oxygen, we have 4 times 2 is 8 oxygens. So that number comes out to, if I did the math right, 399.34 grams per mole. So that would be the formula mass for lead sulfate. Again, it's the same as the last one, just add up the atomic masses of everything in the formula, but the difference here is we have to get the formula first and make sure we're reading that correctly, that we have 2 sulfurs, 8 oxygens when we have 2 whole sulfates in the formula. Okay, any questions on that? All right, so that's how we calculate molar mass. Let's just do another couple examples now where we're going to actually use molar mass as a conversion factor. Okay, so we use molar mass the same way that we use atomic mass. We just use it to relate the moles of a substance to the grams of a substance. So this is an example from work that we did in my group a few years ago. So one of my students that I work with, who's since graduated, a graduate student, made this compound that glows bright red like I'm showing here. And the molar mass of this compound is 774.94 grams per mole. We want to know how many molecules are there in a 1 gram sample. So this is kind of similar to an example we did earlier with an element. Now we're just dealing with a compound instead. And so the steps are really very similar. So if we want to know the number of molecules in this, so this is a compound, which means that the fundamental building block of this is not going to be atoms, but molecules. And that's what we're going to find here. So that's what we're looking for. We start with what we're given. So it's 1.00 grams. I didn't give you the exact formula of the compound, so it's an iridium compound, so we'll just put IR in brackets just to indicate that it's some compound of iridium. We don't know the formula, but we don't need to here, because in this case we're giving you the molar mass directly. So we want to go from grams into number of atoms, number of molecules in this case, but we don't have a direct conversion, so we want to get to moles first. So we want to convert to moles of substance and cancel out the grams. That's why we're going to use molar mass, which is directly given as 774.94. So that number needs to go in the denominator so that grams cancel out. All right, so now we're in moles of compound, and then we can use Avogadro's number to figure out how many molecules there are. So we want moles to cancel, and we're going to calculate the molecules of that substance. And we're going to use Avogadro's number. So in this case, it's a compound, so it's going to be made up of molecules and not atoms. So the Avogadro's number will tell us directly how many molecules are in there. And so from that, we get 7.77 times 10 to the 20th. All right, again, in most contexts, not particularly useful to know how many molecules there are in 1 gram of a substance, but we can calculate it. And the only difference between this and the problem we did earlier is that for elements, which are typically made up of atoms, Avogadro's number tells you how many atoms are in that sample of the element. Here, it's a compound that's made up of molecules. It's a covalent compound, even though it has a metal in the middle, but it's covalent. And so this Avogadro's number tells you how many molecules there are. Again, the number of fundamental building blocks of that substance that are present in 1 mole. All right, any questions so far? All right, the last thing we're going to cover today, so I guess it looks like we'll get out a little bit early, which I'm sure none of you are upset about. The last thing we're going to cover is we're going to come back to this concept of mass percent. So mass percent was one of the first things we learned, if you remember that far back. I guess it was only about a little over a month ago, so not too far back, where we talked about, the mass percent of any substance is given as the mass of one element of that substance over the mass of the entire compound. And at that time, we were just doing it strictly in terms of mass values, grams of substance divided by grams, or grams of element divided by grams of substance, and then using that as a conversion factor at times, but really not doing too much in depth with that topic. So as we review the definition of mass percent, we're not changing the definition, we're just going to change how we can calculate it for a certain substance. So it's going to be the mass of one element in a compound, whatever element we're talking about, divided by the mass of the whole compound, and then multiplied by 100. Okay, so that's the definition of mass percent. That should be a review from one of the first lectures, maybe the first lecture in this course. But what we're going to talk about how to do today, and this will be what we end with, but we'll come back to this a little bit next time in the other direction, is how to determine the mass percent from the molecular formula. So if in the previous part of the course, we gave you directly the masses of the elements in the compound, and you were then from there to determine mass percent. But if we just give you the chemical formula of a compound, or the molecular formula, how I have it stated here, we can also get the mass percent from that. So the way that we do this is we assume that we have 1 mole of compound. Because we have to recall that mass percent is what's called an intrinsic property. It doesn't matter how much of the substance you have. Whether you have one tiny little speck of the compound or whether you have a whole giant pile of it, the mass percent for any element is going to be the same. It's an intrinsic property. It's not dependent on how much compound you have. It's a ratio. That's why that's the case. So for calculating the mass percent from the molecular formula, we assume that we have 1 mole of compound, which means that the mass of the compound, if we assume 1 mole, is its molar mass. 1 mole of compound is to turn that into grams, that would just be the molar mass, and then we have we'll go from there. So then the mass percent in that case can be calculated as the mass of the element A in 1 mole of the compound divided by the molar mass of the compound, which is the mass of the compound that corresponds to 1 mole. And then we're usually doing this as percentages. So this would be the mass ratio, but more commonly it's percent, which is times 100. All right, so we can use the chemical formula and the atomic masses of the elements and the molar mass of the whole compound to get a mass percent. All right, so let's just finish off then with an example of how that works. So going back to the same compound we talked about earlier, glycine, C2H5NO2 being the formula, if we assume 1 mole of this compound, so we're determining the mass percent of carbon in this compound. This compound is made up of 4 different elements. We want to know what percent by mass is the carbon. So if we have 1 mole of this compound, we saw earlier that the molar mass was 75.07. So that means 1 mole of compound has a mass of 75.07 grams. That's the whole compound. That's the denominator in the mass percent calculation. But if we want to find the mass percent of carbon, we need to find out how much of this 75.07 grams comes from the carbon. And what we'll notice is that this compound has 2 carbons in the formula. So the mass, so that means in 1 mole of compound, we have 2 moles of carbon. All right, so again, the subscript 2 on carbon tells us that for 1 mole of C2H5NO2, there's going to be 2 moles of carbon present. All right, so we know the mass of the compound in 1 mole. We know how many moles of carbon there are in 1 mole of the compound. Now we just have to convert this to a mass to be able to use it. So as we talked about at the very beginning of today, or more towards the beginning of today, if we have 2 moles of carbon, we're going to figure out the mass of that. We just use the atomic mass of carbon. So 2 moles of carbon, we're going to do it in grams. Let me write out the unit explicitly. We're looking for grams of carbon. We want moles of carbon to cancel, and so that's just going to be the atomic mass of carbon. So that's from the periodic table. We used that number earlier, but let's refresh up what it is, 12.01 for carbon. Okay, so the atomic mass of carbon is 12.01 grams per mole. We want to find the mass of 2 moles, so we just multiply those two, 12.01 grams of carbon in 1 mole. And so that means this substance with 2 moles of carbon present has 24.02 grams of carbon. And then we can use those two numbers, the mass of the element, the mass of the compound, to get mass percent. So we had 24.02 grams of carbon. The whole molar mass of the compound is 75.07. So of those 75.07 grams that are in 1 mole, 24.02 grams are carbon. We multiply by 100 to get it to a percent, and that comes out to 32.00%. Okay? So if we did the mass percents for every element in the same way, hydrogen, nitrogen, oxygen, add those up, you get 100%. So 32% of that would be carbon. So that's how we calculate a mass percent from a formula. Next time what we're going to do, which is slightly more interesting, a little bit more involved, is we're going to use the formula, we're going to use the mass percents of a compound that we're given to determine the formula. So we can go both ways in this case. So we're going to go backwards next time. And if I didn't have this much time, I would have covered that today, but we'll cover it next time. We'll get out a little bit early today, and that's where we end with. So any last questions before I close up for the week? All right, we'll be back next Tuesday, and we'll continue on with mass percents, just in a slightly different context and other related topics.